Welcome back, Geometry. We are in Chapter 4, Section 8, and we are going to look at coordinate proofs today. So pause the video, try these warm-up questions, come on back and check your answer. Remember, finding the midpoint is basically taking an average, right? So you would add your x values and divide by 2. 0 plus 2y divided by 2 is plain old y, isn't it? And you'd add your y values, 2x plus 2z all over 2, leaving you x plus z. Kind of tricky with those variables, huh? One leg of a right triangle has a length of 12. The hypotenuse has a length of 13. So how did you find this? Yes, Pythagorean theorem. And you should have found 5. The distance between these 2 points, where B is greater than A, distance between them. Using your distance formula, you should have B minus A. Excellent. Okay, so today's objective is to position figures in the coordinate plane for use in coordinate proofs and prove geometric concepts by using a coordinate proof. So today we're talking about a coordinate proof, which is a style of proof that uses coordinate geometry and algebra. The first step in a coordinate proof is to position the given figure in the plane, in the coordinate plane. You can use any position, but there are some strategies that can make the steps of this proof simpler. And here are a few. One thing we can do to make this proof simpler is use the origin as a vertex. When you place your figure on the plane, use the origin. And where is the origin? That's right, 0, 0, right? Keeping your figure in quadrant 1 can also reduce the complexity, right? We could use a different strategy and center the figure at the origin. Or we could even center a side of the figure at the origin. And the final strategy for making these proofs easier is to use one or both axes, the x and y axes, as sides of the figure. So let's try this. We want to position a square with a side length of 6 units in this coordinate plane. Let me add some labels here, x and y. Each blue line is a single unit here. So be sure you have labeled. So again, we want a square with a side length of 6 units. So I could put a vertex of the square at 0, 0, and then go ahead and make a side of unit 6. 3, 4, 5, 6. And I could make the second side going straight up, right? 1, 2, 3, 4, 5, 6. And we need to complete the square by completing the other 2 sides. Awesome. Okay, so there is a square in a coordinate plane with side lengths of 6 units. Let's try a right triangle with leg lengths of 2 and 4 units in the coordinate plane. So we need leg lengths of 2 and 4. So again, we're going to put a vertex at 0, 0. It's a right triangle, so this 0, 0 works really well. There's a leg length of 2, and the other leg length is 4. 1, 2, 3, 4. Okay, and so I have my right angle right at the point of origin, right? And so now we just complete by completing the final side. On paper, definitely use a ruler. Okay, and there we have it. Excellent. Once the figure is placed in the coordinate plane, you can use something, the coordinates. You can use slope. You can use the coordinates of the vertices, right? And there are a couple of formulas that you can use to prove statements about the figure. One is the distance formula, And the other one that you have already used today is the midpoint formula. So let's write a coordinate proof. Given we have a rectangle ABCD with the vertices shown here, we are asked to prove the diagonals bisect each other. Okay, so we're going to go ahead and position this rectangle. We have A at 0, 0. We have B at 4, 0. We have C at 4, 10. And we have D at 0, 10. And let me just make sure my labels are visible for you. Each unit is 10 again. Negative 10. Up here we have positive 10. Okay, so there's our rectangle. To complete it, we may want to draw in those side segments. Right? And we're being asked to prove that the diagonals bisect each other. So let's think about that. I'm going to grab a line, a segment. Let me get a different color. How about purple? And we're going to, I'm going to draw in the diagonals. There's one, right? And here is the second diagonal, hopefully. Something like that, right? So we're trying to prove that those diagonals bisect each other. What does this word bisect mean? That's right. To divide a segment into two equal parts, right? So that's what we're trying to do here. So what we might want to do is use our midpoint formula. So we're going to see if the midpoint of DB is at the same location as the midpoint of AC, right? If it is, then they happen to be crossing right at each other's midpoints, meaning that they're bisecting each other. So we can go ahead and use the midpoint formula. This is another look at the very diagram that we're using. Notice the scale is a little wider in the x-axis than in the y-axis, right? I think. Let's see. It may not look that way in your projection. Sometimes things are stretched a little in mine here. So let's find the midpoint of AC. AC. So do you remember how to find that? We simply use the point 0, 0 and the point 4, 10, right? So we will start with our x values and find their average. 0 plus 4 and divide by 2. And the y values. And that would be 0 plus 10 and divide by 2. So ultimately, we have 4 over 2 and 10 over 2, right? So we have 2, 5. So AC has a midpoint at 2, 5. Let's see where the midpoint is for BD. Once again, we'll use these 2 points. So point D is at 0, 10, and point B is at 4, 0. So let's start with the x's. The x value of 4 plus 0 over 2. And the y value here is 0, right? So 0 plus 10 over 2. And so what do we have? 4 over 2, which is 2. And 10 over 2, which is 5. Yay. They do coincide. These midpoints coincide at 2, 5. And therefore, the diagonals bisect each other. Sometimes we use a coordinate proof to prove that a certain relationship is always true. So this is kind of like forming a rule for all right triangles or for all squares. You can prove that a statement is true for all right triangles without knowing the side length. To do this, we would use variables as the coordinates of the vertices, just like we use variables whenever we write rules, right? So let's position a figure in the coordinate plane and give the coordinates of the each vertex. So go ahead and position a rectangle in the coordinate plane with a width of m and a length twice the width. Okay, so we could imagine this taking place on a coordinate plane where we know the units. So here is a coordinate plane where each unit is 1, right? And so if I make a rectangle here starting at the point of origin, 0, 0. I could make a rectangle that has a width of something. So let's say it has a width of that far. And that, you see here, is 4 units, right? But I'm going to say that that is m. It has a width of m. And the length now is twice the width. So if I'm going to show the length, I'm going to go vertically, straight up, right? And I'm going to go not just 4, but I'm going to go 8 units. But I'm going to call that 2m, right? So this is one way that a rectangle could be positioned in a coordinate plane. And using variables rather than units, imagine we remove the units, right? But you see the scale here, that I have a width of m and a length of 2m. We can show it without the grid behind it, as they do here. So here we go again. They started at 0, 0. Notice that they showed a length horizontally. So this is just another way to show it. And a width vertically. Okay, one thing I didn't do, which they're showing you, is labeling each vertex, right? So on mine, we could label at 0, 0. And notice when we get to this second vertex over here, we've traveled m, and we have flown nowhere, right? M0, which is, similar to what you see here, where our orientation is just, our rectangle is kind of pointing up, and theirs is laying flat, right? On ours that we originally drew, when we look up here, this upper left vertex, we have walked nowhere, but we flew to m, right? To m. And finally, this last vertex out here, we walk an m, and we flew a 2m. So you don't need both of these, but you need one of these in your notes, okay? 2 correct answers to the same question. So let's try this again. Now we're going to position a figure in the coordinate plane and give the coordinates of the vertex, each vertex. So go ahead and do it with a right triangle with leg lengths of S and T. Come back and check your work. Remember to label each vertex. All right, so here is one correct answer, and there are others. But on a coordinate plane, you could place the right angle at 0, 0. And let's imagine the legs of length S and the leg length of length T, right? And so notice that when you label the vertices, if you called this side here length S, then you would have the coordinates at 0, S, walk nowhere, fly S, right? And if you label the lower leg as T, then you would walk T and fly 0. So T0 would be the vertex. Now, you could have used the letters in the opposite locations, right? And there are other ways to look at this as well. Watch out here. Do not use both axes when positioning a figure unless you know the figure has what type of angle? Good, a right angle. We have been using both axes, like here and here, because we know that a right triangle and a rectangle have a right angle. Okay, let's try one more. Position a square with side length 4p in the coordinate plane and give the coordinates of each vertex. So here's my x-axis, here's my y-axis. And so we're going to position a square with side lengths of 4p. I'm going to place a vertex at 0, 0. And we're going to go such a distance to the right. And now that I have walked, I'm going to say I've walked 4p and flew nowhere, right? My y value is 0. Now I'm going to go vertical. Square, right? Try to walk about the same distance. And now, fly. I flew, I walked 0 and I flew 4p, right? Now we're going to complete our square and name this final vertex, right? It should look like a square. Now to get to this vertex here, you would have to walk 4p and fly 4p. Right. Awesome. I hope you're getting the hang of this. If a coordinate proof requires calculations with fractions, choose coordinates that make the calculations simpler when you can. For example, use multiples of 2 when you are to find the coordinates of a midpoint. Once you have assigned the coordinates of the vertices, the procedure for the proof is the same, except that your calculations will involve variables. Okay, let's jump to this proof. Given that we have a rectangle, PQRS, let's prove that the diagonals are congruent. Okay, so the first step would be to give each vertex coordinates. Okay, and so we could say that P is at like 0, B. So we fly B, right? In that case, S would be at what? That's right, 0, 0. R would be out here, and if we used B, how about if we use the letter that comes just before it? So let's walk A, right, and fly 0, so A0. And in that case, to get to Q from 0, 0, we would walk A and fly B, okay? So there we go. We've now positioned this figure on, imagine, on a coordinate plane. There's your x-axis, there's your y-axis. This is A length, this is B length, okay? Good. So now we kind of have a way to look at this. And so we want to determine whether the diagonals are congruent, right? The diagonals. So we would use our distance formula, right? We would use our distance formula here to find the distance between P and R. And then we would use our distance formula to find the segment SQ and see if they measure the same length, right? By the distance formula, here we have, look at this, we have a right triangle. We're finding the distance between S and Q. So again, it's just using the Pythagorean theorem, isn't it? It would be the square root of A squared plus, what's this distance? That's the distance of B squared, right? And the same is true for PR. Look at this, we have B squared plus A squared equals C squared, right? Or the square root of A squared plus B squared. And so they both have the same measure, and thus they are congruent. Okay, pause, try these, and come back and check your work. Possible answers for 1 are, for 2, good job. And try this, come back and check your work. And there you go.